Elitza Hristova. You'll be talking on topics of really important associative algebras.
Thank you very much. First, I would like to thank the organizers for the invitation to give a talk on this very nice conference. I'm really honored to be here among so many young women. I want to say now that we're going to completely switch the topic from the first two talks. The first two talks were very nice, geometric ones, and unfortunately, now we have to go to algebra. And for some people, unfortunately. Yes, so the topic of this talk comes from the theory of algebras with polynomial identities, or shortly PI algebras, and its relations with representation theory. So first we'll introduce the notion of a PI algebra and give some starting examples. Then we'll introduce the class of PI algebras that we'll be interested in, namely the nilpotent associative algebras. And then we'll discuss the GLN module structure of some of those nilpotent associative algebras. And we will see that PI algebras in general, they are associative algebras, but not necessarily commutative. And in terms of GLN module structure, we'll see that this class, the nilpotent ones, is the closest among all PI algebras to the commutative ones. And in the end, we'll discuss some tensor product theorems for nilpotent algebras. So let me start with the definition. In the beginning of the talk, K will be a field of characteristic 0. Towards the end, when we talk about tensor products, we'll relax this condition and we'll consider any field. But for now, it's a characteristic 0. And here are some standard notations from algebra. So we take X to be an infinite set of variables, and by K of X, we'll denote the free unital associative algebra generated by this set X. And then we say that an algebra A satisfies a polynomial identity if we can find a non-zero polynomial inside K of X, such that when we evaluate this polynomial with elements from the algebra, we obtain always 0. And if A satisfies such a polynomial identity, A is called a PI algebra. And there are some natural examples to get a feeling what PI algebras are. So, for example, every commutative algebra is naturally a PI algebra because all the elements just satisfy the commutator identity. And actually, PI algebras are considered generalizations of commutative algebras, and the notion of polynomial identity is considered to be a generalization of the notion of commutativity. Also, finite dimensional algebras, so they are also naturally PI algebras, because if our algebra is of dimension R, then it's not difficult to see that if we take this alternating sum of R plus 1 product with R plus 1 terms, where S is the symmetric group. So if we take this alternating sum, then it necessarily vanishes on all elements of the algebra. Okay, here are some more examples. For them, we'll need the notion of a long commutator. So we start with the usual double commutator, and we define a commutator of length P recursively using this formula. Then we have more examples that satisfy such commutator identities. If we take E to be the exterior, or also called the Grassmann algebra, over a countable dimensional vector space, and ER to be the Grassmann algebra over an R-dimensional vector space, then both of them, it is not difficult to see that they satisfy a triple commutator identity, because all the elements of even degree inside, they are central. So yeah, from there it follows that the triple commutator identity holds. And also, if we take a tensor product of an infinite and a finite dimensional Grassmann algebra, we again obtain a PI algebra that satisfies this long commutator identity. So these examples will be related to the rest of the talk, and the last example is not related, but I thought it might be interesting for the audience here. So it was recently proven that if we take the path algebra of a finite quiver, then it will be a PI algebra if and only if every vertex of the quiver lies in at most one oriented cycle.
May I have just
Yeah.
a notational question?
Mhm.
You say triple product, but this is, you have three elements and you're doing twice the commutator.
Exactly, yes.
Okay. So
yes.
this is actually some nilpotent
Yes.
nilpotent
Yes.
algebra.
Yes, yes, this is also the name, nilpotent.
Yeah.
Yes, so any algebra that satisfies a long commutator identity is called nilpotent. And if the commutator identity is of length p plus 1, then the algebra is nilpotent of index at most p. Yes, they are quite related to the important Lie algebras, right? This looks like the lower central series, but now we take this in the associative case, not in the Lie case. And okay, so that would be the class of algebras that we are interested in. And now we will introduce some more terminology that we need for the study of these algebras. An important notion in PI theory is the notion of a T ideal. So this is an ideal inside the free associative algebra that has additional properties. That it is closed under all K algebra endomorphisms, or in other words, it is closed under all substitutions of the variables with elements from the algebra. And why do we care about such ideals? Is because that if we take PI algebra A and the set of all polynomial identities that are satisfied by this PI algebra, then this set will form a T ideal that will denote by a T of A. And also conversely, if we take a T ideal, then we can construct a PI algebra such that this T ideal is exactly the T ideal of identities of this algebra. So the two things could be equivalent definitions of a T ideal. And for example, in our case, we'll be interested in this series of ideals where I2 will be the usual commutator ideal, so the ideal generated by all commutators. And then I3 will be the ideal generated by all triple commutators, and so on. IP will be the ideal generated by all commutators of length p. These are all T ideals. And we can reformulate the definition of a nilpotent algebra in terms of T ideals. One algebra will be nilpotent of index at most p if the polynomial, the T ideal of polynomial identities of A contains the ideal I plus 1, the ideal generated by commutators of length p plus 1. Okay, and the last notion that we need is the notion of a relatively free algebra. So when we start with a PI algebra or with an ideal, T ideal, then we can build the following quotient, where now we take a finite rank free associative algebra. We take a finite subset of our initial set, and we take the free associative algebra generated by this finite subset. Then for any n, we can do this for any n, and we take this quotient, where this is the intersection of our T ideal with our free associative finite rank of free associative algebra, and this quotient is called the relatively free algebra of rank n in the class or variety of all associative algebras that satisfy the identities from I. When we take T ideal and we take all the algebras that satisfy the identities of this ideal, this class of algebras is called a variety. And in this variety, there is one free object. This is the relatively free algebra. And we'll denote this intersection again by I for simplification. So from now on, you'll see in the quotient just the ideal, and it will be understood from the context whether it's the whole T ideal or the intersection with K of Xn. So one very simple example here, if we take the commutator ideal, then our relatively free algebra is actually the symmetric algebra of the vector space Vn, where Vn is the vector space with basis x1, xn. Okay, and okay, this is enough for definitions. We now want to introduce some representation theory inside, but a very classical one. We take a classical general linear group over the field K, and then it naturally acts on our vector space with its fixed basis, and we extend this action to the diagonal action on the whole field associative algebra. And since I is a submodule, GLN submodule, this algebra inherits the GLN module structure of K of Xn. And one central question in the theory of PI algebras is to determine the GLN module structure of this quotient for different T ideals I. Why is this question important? Because often it is easier, instead of studying the identities themselves, to consider the dual problem, study the quotient and study the so-called non-identities of the algebra. And if we find a nice description of the non-identities, then this will help us to also determine the identities of the algebra. And so that's why this is an important problem in the theory. And in this talk, we'll be interested in the case when our T ideal is generated by commutators, or more generally, if it contains the ideal generated by long commutators. And this structure, the structure of K of Xn modulo the ideal IB plus 1, is known for small values of P. So let me give it how it looks like for P equal to 1 and 2. So we'll give all the decompositions pictorially using Young diagrams, the Young diagrams of the corresponding partitions. So we take a non-negative integer partition in at most n parts, and we denote by v lambda the reducible GLN module that corresponds to this partition. So there is a Young diagram corresponding to lambda, and in the case, as I said, we express the decomposition in terms of Young diagrams. So the first case is the usual, as we said, symmetric algebra. So this is very classically known that the decomposition includes all Young diagrams consisting of one long row that grows arbitrarily. And then this is also quite classical. The case P equal to 2 is also quite classical in the theory of PI algebras. Here, the decomposition, the GLN module decomposition of this thing is given by such hook-shaped diagrams with one long row and one long column. And actually, this shape of diagrams is also the general shape for all relatively free algebras. So we have the following theorem of Mitsur and Regev. This is a classical theorem. It's also called the Hooke theorem. It says that for any T ideal, if we take the decomposition as a GLN module, and if we take a V lambda which appears with a non-zero multiplicity inside the decomposition, then there exist, first there exist two integers. So for any T ideal, there exist integers K and L, such that all lambda that correspond to non-zero multiplicities, they are supported in diagrams of this form, which means that we have no restriction on the first k column, k rows of the Young diagram, but from the k plus first column, this condition holds that the number of boxes should be less or equal to L. And then Barrel improved this theorem in 2006, saying that actually the diagram looks like this. So for any T ideal, we have 4 integers with this condition that omega 0 is always greater or equal to omega 1, such that the first omega 0 rows of the Young diagram can grow arbitrarily large. Also, the first omega 1 columns can grow arbitrarily large, and the rest are bounded in this rectangle with sides S1 and S2. These are the conditions for non-zero multiplicities. And Vero also show that when our T ideal is equal to the commutator ideal, then omega 0 and omega 1 are equal to 1, the long commutator ideal. In the case P equal to 1, then as you saw previously, omega 0 will be again 1, but omega 1 is 0 because their diagrams were just rows without anything. And starting from P2 or greater, we also have one long column in the beginning.
May I ask something?
Yes.
Because when this P is 3,
Yes.
you have just the hooks,
Yes.
but they all appears. So you expect for, every non-zero multiplicity, every diagram which is in this hook has non-zero multiplicity.
No, not every diagram which is in this hook, just that all the diagrams which appear with non-zero multiplicities are inside, but this form itself, it doesn't appear, it just contains all the diagrams. For some of them, this bound will be reached, but then that bound will not be reached. For others, this will be reached. You'll see in examples for equal 3 and 4 that, for some of them, that bound exists, and yes, but this is bound for all of them.
Okay.
And not all the partitions that satisfy this bound have to be in the decomposition.
Yeah. Good.
I think his question is whether you can whether for every shape like this you can find an example of I, so that all Young diagrams that fit to this shape would appear for that concrete T ideal I.
For every shape, you mean for every
Choice
choice of these numbers?
Yes.
This is not known because for many I's, we actually don't know those numbers. So I don't know.
Some easy bounds that are coming from the dimension that you can remove by taking more variables, by increasing n. So,
They shouldn't depend.
my question should be, can we remove some of these bounds by increasing n? But it's not. Well, you can, in the case P equal 3, you can have something like, I don't know how it's called, inductive limits or something like.
For
Yeah.
people 3.
Well, these hooks that
Yes.
you showed the previous slide.
Yes.
You have-
This one?
Yeah, this one.
Mhm.
If n is big enough, you have,
It's the same.
you're pushing the bound further away, no?
Yes, that's true, but it's the same shape, just
Same shape,
n
yeah,
rows.
but somehow you have all the hooks in limit n equal to infinity.
You have all the hooks of this shape,
Yeah,
yes,
And
that's
so the
true.
question,
But,
my question should be, can you by increasing n, can you say that you can remove S1 and S2?
No, S1 and S2, you cannot remove by making n
Well,
larger.
something else. Please.
The dimension of n is here. So when you increase n, this row increases here, this column increases and gets bigger. But S1 and S2, they remain the same for all n.
Right, same.
Yes, they don't depend on n. This here gets larger.
Yeah.
So in your example here, that column corresponds to that thing here. They're actually here S1 and S2, they are just one. And this one doesn't change. When n grows, this is still one. We don't get another box here or another box here.
Thank you.
Yeah, sure.
I had a related question.
Mhm.
Is there an operation on PADLs that corresponds to transposing a Young diagram?
Hmm. Uh-huh.
Yes, you have multiplication by alternating representations.
Actually, shouldn't be the case because this is bigger than that. And if you transpose,
Okay,
then that would be there and it will violate the
Yes, yes.
theorem. So probably in the case when they are equal,
Mhm.
you might, I don't know, but in the general case, no.
Understand, yeah.
Okay, yes, so this is a very nice theorem. And our first contribution is that we'll compute S2 in this case, when I is the ideal, I p plus 1. But first we need one more notation. We will introduce an important subalgebra of K of xn, and that would be this subalgebra of proper polynomials. How is it defined? So we first take commutators, pure commutators, to be just commutators in which every element is from the set Xn, not a polynomial or not a linear combination, but just these are pure commutators. And by Bn will denote the subalgebra generated by all pure commutators. So the elements will be products and linear combinations of products of such things. It is in general an infinite dimensional subalgebra. And it is also a submodule, a GON submodule. And by Bn of I will denote the image of Bn under this natural projection. And there is the following theorem that says that we can reduce the problem of studying the GLN module structure of our quotient K of xn mod I to studying the GLN module structure of the subalgebra of proper polynomials, and then using this tensor product representation. And then once we know the GLN module structure of this group, we can use little Richardson branching rules to obtain the decomposition of the whole quotient. Here again, Vn is the vector space with a basis xn. And in the case when I is equal to ip plus 1, we'll use the simpler notation Bnp and not Bn of ip plus 1. So that will be the subalgebra of proper polynomials inside the relatively free algebra K of xn mod ip plus 1. And here is our first result. If we consider the GLN module structure of the subalgebra of proper polynomials, in the case when our T ideal is the ideal generated by commutators of length p plus 1, then this now is a finite dimensional algebra, and we have the property that lambda 1 is less or equal to p minus 1. So in every Young diagram, the first row can contain at most p minus 1 boxes. And using little Richardson formula, we can reformulate this condition for the whole relatively free algebra. And the condition now is the following. D lambda appears with non-zero multiplicity in the decomposition if lambda 1 is not restricted, but lambda 2 obeys this condition. So lambda 1 can grow arbitrarily large, but lambda 2 is bounded by p minus 1. So in the theorem here, that says that S2 is equal in this case to p minus 1. So for this ideal, we know that omega 0 is 1, omega 1 is also 1, and we also know the number S2 that is p minus 1. It is also important that this bound is actually sharp. It is always obtained. As we can see on these examples here, that are also known, computed from before. The GLN module structure of BN3 was computed by Volinchenko long ago. And we can see that this is a finite dimensional algebra. And in the first row, we can have at most two. So in this case, P minus 1 is 2. We can have at most two boxes. And the next case was also computed. It looks more complicated, but still obeys the same rule that in the first row, we can have at most P minus 1 boxes. Okay, and again, this is a finite dimensional algebra. And it is also interesting that being finite dimensional, that BNP is finite dimensional characterizes completely the class of nilpotent algebras. So we have this result that if A is API algebra, then the subalgebra of proper polynomials is finite dimensional if and only if A is nilpotent. If it is not, then it is infinite dimensional. And this theorem, using little Richardson coefficients, translates into this, that omega 0 in Bernoulli's theorem is equal to 1 if and only if our algebra A is nilpotent. So in this picture here, if A is not nilpotent, here we'll have at least two rows. And if A is nilpotent, even if not corresponding to this ideal, but to some bigger ideal, then we'll have always just one row here. Okay, and so in this way, we can say that the class of nilpotent algebras is the closest to commutative, because for commutative case, this is just one dimensional. And in the nilpotent case, it is a finite dimension. Okay, so this is about this part. And okay, there is a short idea of the proof. For the finite dimensionality, we use properties of products of commutators. Let me just say the first one, that if we take commutator of length M1 and multiply it by a commutator of length M2, they will necessarily land in the ideal generated by commutators of this form. So, and from there follows finite dimensionality, because if we multiply enough many commutators, we'll reach our quotient. And so we reach 0. So we cannot get too many products of commutators. And for the rest, for the other part, if A is not nilpotent, then one can show that there is a surjective map from our quotient to the relatively free algebra, where the T ideal here is the T ideal of identities of the 2 by 2 upper triangular matrices. And this T ideal is known and well studied. And the subalgebra of proper polynomials there is infinite dimensional. So whatever you have started with, when you surjectively project it here, it still will be infinite dimensional. And these are the two steps to show the two parts of the theorem. And now we go to the last part of the talk, which will be tensor products of nilpotent algebras. With the help of tensor products, we'll build new examples. So far, we have given few examples of nilpotent algebras. We gave the example of the Grassmann algebra, the countable over a countable dimensional vector space, and the Grassmann algebra over a finite dimensional vector space. We recall that they both satisfy the triple commutator identity. And it will be also important that the finite dimensional ones satisfy also a product of double commutators of this form. And we also said in the beginning that the tensor product is again nilpotent. And there is a more general statement that if we take any tensor product of this kind, where the first algebra is infinite dimensional and the others are finite dimensional, or all of them are finite dimensional, then this particular product is again nilpotent. And in general, we don't know the index of linear potency, but there are some cases in which we know if we take this product, then this will satisfy commutator length 4, and these two products will satisfy a commutator of length 5. And there is here a natural question: when do we get that? When do we get that the tensor product of two linear potent algebras is again linear potent? Because if we take two commutative, then the tensor product will always be commutative. But here it's not always the case. There is a very simple example. If we take the infinite dimensional Grassmann algebra and multiply it with itself, then this is not linear potent. So we need some conditions on the algebras in order to show that the tensor product is linear potent. And there is the first statement by Deriavina and Krasjunikov. It holds over any field, not only characteristic 0. It says that if we take G and H to satisfy a triple commutator identity, and also H to satisfy a product of double commutators, just like the finite dimensional Grassmann algebra, then necessarily their tensor product is linear potent and satisfies the commutator identity of this length. And from this proposition follows immediately the corollary that we also gave as an example in the beginning, that this tensor product satisfies this commutator identity. And with the same methods, though it was not mentioned in the paper, one can show that if we take the tensor product of two copies of the finite dimensional Grassmann algebra on 2K generators, then that would satisfy this relation. And we extended a bit the theorem of Deriavina and Krasjunikov. We take G to be arbitrary linear potent algebra and H to be the same as before. It will satisfy a triple commutator identity and a product of double commutators, and then their tensor product will be again linear potent, but this time we don't know what will be the index of linear potency. And we saw that this condition cannot be completely drawn. We need to have some condition on at least one of the algebras to verify, to be sure that the product will be again linear potent, but we can replace it with something probably not so technically looking. It follows from results, old results of Jennings and Watishev, that if H is finitely generated linear potent algebra, then it will satisfy a product of this form. So that proposition can be reformulated in a slightly probably more understandable way, that if G is any linear potent algebra and H is finitely generated and linear potent of index at mode 2, then the tensor product will be again linear potent. And so the only disadvantage here, well, one disadvantage is that we don't know the index of linear potency, and would be good to have it. So if we restrict further H, this H here, so we keep G the same, but we restrict H to satisfy just the product of two commutators, then we can compute the index of linear potency of this product. But here, this now proposition has the condition that the characteristic should be different from 3, because it uses this result of the Deriavina and Krasjunikov, that if we take a commutator, the ideal generated by commutators of length P, and commute it with two elements from K of X, we land in the ideal IP plus 2. That result holds only when the characteristic is different from 3. If it is equal, then we can guarantee only this inclusion, but not the above one. And that is why in this proposition we have this restriction. And okay, using this proposition, we can build explicit examples in which we compute the index of linear potency. And when we use the proposition, of course, we have to have this condition, characteristic different from 3. So when we take E, this condition here is satisfied by the algebra E2. So we can always multiply by E2, and we will know what we get as an index of linear potency. So if we take E as the starting algebra as our G and multiply it by as many copies as we want by E2, then we know that this would be the resulting index of linear potency. And we can also show that this is the minimal length of a commutator that is satisfied. Also, if we start with this algebra, for which we know the index of linear potency, and we again multiply it by some copies of E2, then we'll know the index of linear potency of the result. And when we just take copies of E2, E2, the proposition will not give the minimal length of commutator, so we compute it separately, and we get that this is the minimal here. And so it will be good to know whether this condition K different characteristic of K different from 3 can be dropped, because it seems that these two should hold only also in that case, but we cannot prove it so far. And with the help, why is it important to have explicit examples where we know the index of linear potency? Because with the help of them, we can generate explicit modules inside the GLI module structure of BNP. Before that, we were considering bounds on the structure of the partitions. But now, having explicit algebras that satisfy fixed satisfy fixed commutator identity, with the help of these algebras, we can give explicit families of partitions that participate with non-zero multiplicity in the structure of a BNP for any P. This is, of course, not the complete description. It is out of reach to describe completely the GLI module structure, but at least gives some information. And here, how do we use these examples? I don't know if, okay, just very briefly for the first one. Since we know that this algebra satisfies that identity, it follows that if we find a proper polynomial that is non-zero in this algebra, then it will not be an element of our T ideal, and therefore it will be a non-zero element of BNP. So if we start with the highest weight vector that is not a zero element for this algebra, that would be a non-zero highest weight vector inside BNP, and so it will generate an irreducible GLN module that will appear with non-zero multiplicity and BNP. And so for the different families of partitions, we just use different algebras and construct explicit polynomials that generate irreducible GLN modules. And let us give an example, because that's not very informative here. So we know the description, which I proved, there is the description for P equal to 4. With our methods for P equal to 5, we add some more partitions to the GLN module structure. Every next BNP contains the previous one, of course, because the ideals are nested, polynomials or the commutators of length P, they contain the commutators of length P plus 1, and that's why BNP contains Bn4. But there are some more partitions that appear. The black ones were known from before, and now we add the blue ones here. And this is only an inclusion, not a complete description of the structure. But here we see that there is not much difference, at least from what we have found from Bn4 to Bn5, because this is a relatively small number of new partitions, and all of them are of fixed length that doesn't depend on n, on fixed size, sorry, the number of boxes. doesn't depend on n. But when we go from BN5 to BN6, the picture is completely different. There are many more new partitions, and their number grows with n. And so here comes the question of asymptotic equivalence. If two, it's an asymptotic equivalence for T ideals, but translated in the language of proper subalgebras of proper polynomials, asymptotic equivalence would mean that the two things are the same, contain the same polynomials of large enough degree. For small degrees, like here, they are different, but for large enough degree, they contain the same polynomials. Here we see from this picture that these certainly are not asymptotically equivalent. And there is now the definition, exact definition. Two T ideals are called asymptotically equivalent. As I said, if for sufficiently large n, they contain the same proper polynomials of degree n. Or equivalently, the corresponding subalgebras of proper polynomials contain the same polynomials of degree n. And from the description of the GON module structure of BNP for the small values of P that we know, it follows that I3 and I4 are asymptotically equivalent, but I4 and I5 are not. And with my colleague Tiago Castillo de Melo, we asked the question whether this can be generalized for larger values here. And we saw that this part, the B part, is easily generalized. So if we take the ideals I2k and I2k plus 1 for any k, they are not asymptotically equivalent. However, we don't know whether the first one generalizes. We would like to know whether these two are asymptotically equivalent. There is evidence, like here, it's not a complete evidence, but at least not a disproof. So there is evidence that this should hold, but for example, we don't know the answer. And that would be the end of the talk. So thank you very much for that.
And are there any questions?
So I wanted to ask for the formulas where you relate BN4 to BN5 and so on. Those really come with multiplicity 1 on the right hand side, or
It's a good question. There start to appear multiplicities. It's just not visible the way I wrote. But if you see BN4, this module appears and then it appears again.
Okay.
So in BN5, we already have multiplicities. But somehow we think that the multiplicities will stay in the low dimensions. So we hope that for modules like this, where n is big, where the size is big of the partition, we hope that there will be no multiplicities, but there is no proof. In the multiplicities appear.
Okay.
That's the short answer, but that could be only in small degrees.
Does it make sense to distinguish Young diagrams where the multiplicity goes to infinity and where it's bounded when the second index goes to infinity? Like, for this question hasn't been.
In this question, this index goes to infinity?
Yeah. When this index goes to infinity, you can ask the question whether a given Young diagram appears with a bounded multiplicity or the multiplicity goes to infinity. And in this case, you're showing a certain Young diagram that it looks like multiplicity will go to infinity.
I think that if P becomes greater than N, then that will be quite a degenerate case, and actually there will be very few partitions.
I see.
But I'm not sure this is, I have to check, but at least in small dimensions, I think if P is greater than N, then actually there are very few modules. So N should be bigger than P. That's the degenerate case, and P is bigger.
I can probably make a short comment, but
Yep.
my feeling that here you need some extra structure. You're in the realm of associative algebras, but you can use Birkhoff, Birkhoff theorem and think of associative algebra as the universal enveloping of the three algebra.
Yes.
And then you have cut on the primitive, in the, so you have Hopf structure already, which is an extra structure. And the primitive elements with respect to this Hopf structure will be maybe giving additional, here we have primitive and product of primitives and so on. So you can probably analyze the problem on this level with an extra Hopf structure. And that can reduce the complexity that you have now. Because
But I is not a Hopf ideal. I is just an ideal of an associative algebra. The T ideal I, it's not a Hopf ideal. It's an ideal of an associative algebra.
Yes.
It's not gonna be preserved under the coproduct. That's the problem.
Okay.
I mean, the Fourier algebra is used a lot, but
Mm.
Hopf structure is not yet being introduced here.
You're writing the identities by iterating the bracket.
Yes,
Why this is not how?
this I don't know,
Okay.
but I can check later, yes, but this is just one example. TADU is something more general than just iterating.
Well, in the case of equals 3, this certainly works, because I did it. But then if you go beyond, I have to see, I don't see what's the problem. I think it's a Hopf ideal.
But any TADU or just this one that is generated by commutators?
I'm talking about conflict.
Only commutators.
I'm talking about.
Okay, I will take a look, yeah, thanks.
I think any questions? No, well, let's think of it.